so let's start off today, right now, working with some examples from our derivative rules, right? Our derivative polynomials, and then also, as I mentioned with the last video, also trying to get into that idea of the derivative of our exponential function. Okay, so let me start to share my screen, and we'll get going. Let that warm up. I'll start to write my title. All right. Okay, there we go. So I want to do some examples of our derivatives of polynomials and looking at the derivative of exponential functions, our natural exponential in particular. Okay. All right. And so just to recall, think back. Then I take the derivative of that x to the n power. I'm going to get n times x to the n minus 1. Okay. Getting that. Likewise, the derivative of a constant, 0. Derivative of our x to the first, our linear term, 1. And then if we happen to have a constant in front, we bring that constant out, multiply our derivative of that function times the constant, or c times f prime of x. And lastly, all these rules to write and remember. The sum or difference, I'll sneak those together. We can just worry about taking the derivative of those functions individually and keeping that same addition, subtraction between, or likewise bringing that prime notation, f prime of x minus g prime of x. Okay. All right, so with that said, again, as we start to go through, we'll start to collapse some of these steps, but I might be a little bit more formal and particular about it as we begin. So for example, let's say we're given y is equal to 3x to the 4th power plus 6x cubed minus 7x squared plus 5x minus 9. So again, I'm not going to worry about trying to factor, simplify, factor anything out. Okay. If you can, of course, combine like terms if that was there. But all I want to do, let's find y prime, right? Or another way of saying, let's find dy dx, right? Or differentiate. Just different ways that might be phrased, okay? And so kind of bringing that notation, I'm gonna be a little redundant here, so bear with me. There's my equation. So now I'm gonna take that derivative. So on each side, taking the derivative with respect to x, that's my independent variable. Derivative of y, the derivative, the dx derivative with respect to x, right? With respect to x, that's what we're kind of saying here. I should bring in that statement as well. Right, that's what everything depends on, is this variable x, so it's with respect to. Okay, and so here, taking that derivative, there's our dy dx, or y prime. I can use that notation next as well. And really what I'm going to say here, initially, since I'm just taking the sum and difference, the adding, subtracting, we can use our sum and difference property, our sum and difference rule, and just separate each sum and difference into their own individual derivative. And again, I made this polynomial 5 terms, so I need to make sure I have these 5 derivative, sneaking this last one in there, actions, operators, following. And again, keeping track of our signs, our positive, negative, our adding, subtracting between each of those terms, right? So in that step, we're going to separate the sum and difference. Okay, so breaking that apart, we'll say. And now, this dy dx or y prime, right? Either one of those notations is perfectly acceptable. Now what we're going to start to do with some of these, now we have coefficients, right? So all those powers, sorry, that's the next step. All those constants, those coefficients can come out front. And that constant I'll leave alone, right? It's not attached to an x per se. But here we get 3 times that x to the 4th. Plus, keeping track of the sign, 6 times the derivative. I know it's a lot of color changing here, but just trying to get this set up. Minus the 7. The derivative of that variable term inside, plus the 5 comes out, times the derivative that's left of our variable term, and then minus the derivative constant. Right, but what's left over, I brought up my coefficient, x to the 4th, x cubed, x squared, right? Typically in that decreasing order, x to the 1st, and I'll keep that constant 9 inside. Right? So I'm going to say here, we're going to bring out the constant coefficients from those variable terms. And last but not least, now we're going to get our power rule showing up. And of course, this one's just a constant. Okay. So I hate to have to separate pages, but getting back into it. Okay. So my y prime is going to be 3 dx of x to the 4th power plus 6 dx x cubed minus 7 dx of x squared plus 5 dx of x minus the derivative of just 9. Okay, so copying that down. And like we mentioned, the power rule, right? So as I go through, my dy dx or my y prime is going to be equal to, again, 3 up front. Now the power rule. I'll keep in parentheses now. The power comes down 4x, 4 minus 1, 3. 4x cubed plus the 6 3x squared, right? We did that one with the limit before. 3 comes down, 3 minus 1, 2, x squared. So 3x squared minus 7 derivative of x squared to x to the first plus that 5 coming down. Derivative of x to the first is just 1, that linear term. Finally, minus, and now the derivative of that constant is 0. Okay. So now finally, multiplying out our dy dx, our y prime, 3 times 4 is 12 x cubed, 6 times 3 plus 18 x squared, minus 7 times 2 minus 14 x to the first, plus 5 minus that 0. So there's our derivative of that original polynomial function. Zoom out a little bit. That 3x to the fourth plus 6x cubed minus 7x squared plus 5x minus 9. That derivative, 12x cubed plus 18x squared minus 14x to the first plus 5. Right, that constant term, the minus 9, when you take its derivative, zeroes out, it disappears. That x to the first, that power rule, when you take its derivative, goes to 1, it disappears, if you will. Just the coefficient 5 is left. All those other terms, the power rule reduces those exponents. X fourth becomes x cubed, x squared down to x to the first. And then those coefficients are just going to interact with the powers we're bringing down to create this new expression. So as we get more comfortable dealing with these polynomials, right, we can jump from this line down to here, later on even this line down to our answer fairly rapidly. Okay, let's do one more quick example there. Let's differentiate g of x is equal to 9x to the fifth power minus 2x cubed plus 7x minus 3. Right? So I want to differentiate here. So that means in our answer, dg dx, or probably more common, g prime of x, right? And so now as we start to go through, kind of sneaking this information, perfectly fine. Choosing one of those, most likely g prime of x, right? Starting off 9, and now our coefficient in front, our variable from x to the fifth, our power rule here, 5x to the fourth. Then minus 2, power rule here, 3x squared plus 7, right? Keeping as constants those coefficients. The derivative of x to the first, 1. And again, that's again another power rule, or that linear term. But then lastly, that constant is going to be 0, or likewise later on we'll just ignore it, we'll just drop it off completely. But for now, that constant term, we know there's no variable, it's going to go to 0. So finally in the end, our derivative, g prime of x, 9 times 5, 45, x to the fourth, Negative 2 times 3, negative 6, x squared, plus 7 times 1, 7. That 0 goes away. Just like that. Okay. And those polynomials, hopefully, will become fairly rapid for us, but it does take some time to watch out for our coefficients, those signs, multiplying by that original exponent, right? Dropping the exponent down by 1, just those little tedious parts we have to be clear about. Okay? All right. So with that said, let's introduce then this next one. So for our derivative of that kind of more natural exponential function. Okay, right? In general, our exponential function f of x is b to the x, right? So now what's important here, we have our constant base, the value being raised to a power, and a variable exponent of variable power. In our polynomials, it was the variable that was the base, a constant as power. Now we've reversed it. And so then here, e, our natural number, right, that we see a lot in our sciences, biology, physics, chemistry, so on, okay? Approximately 2.71 something, something, something. Okay, kind of like pi, it's just a constant. And so then for our exponential function with a natural number as its base, we have that e to the x. Okay, what I'll kind of call my natural exponential function. But lazily, we still call it an exponential function. Okay. In the book, they have this derivation. I'll let you look at that. But what's key here for our differentiation rule that when we take the derivative d dx of the exponential function, it's equal to the same exact exponential function. All right, we get the same exponential as our result. Okay. So, for example, if we have that y is equal to e dx, then y prime is equal to e dx, right? Or dy dx is that e dx. Nothing too tricky with our original exponential, right? And so then if we start to incorporate a coefficient, is say like 3 e to the x, and we want to find f prime at x, right? So if we go through our action, taking our derivative, okay, derivative d dx of 3 e to the x, right? That coefficient comes out, times the derivative of that e dx. Three stays. The derivative of e dx is just e dx. So in the end, f prime of x, the derivative of 3 e dx is just 3 e dx, the same function out. That coefficient just follows us. Derivative of e dx still there. Nothing too tricky. Okay, we'll of course build on that, make it a little more complex later, but for now, thank goodness, nothing much goes on with that derivative of our exponential. All right, I know we're kind of rapid, but I'll let you kind of take that in, post these notes and whatnot. If you have any questions, trouble with that, please share, let me know. All right, take care, see you all soon.